the ArchSoc YouTube live events for the last couple of talks. I've got Hayley Cawthra with me, and she's the chief scientist at the Council for Geoscience in Cape Town, where she initiated and is leading a countrywide continental shelf mapping program. Her other responsibilities include involvement and or leadership in government projects to do with geopolitical borders and deep seabed mining, conducting independent and collaborative research, and training junior staff. Hayley is also a research associate in the African Centre for Coastal Paleo Science at the Nelson Mandela University in Port Elizabeth, where she conducts research and supervises postgraduate students. She holds a PhD from the University of Cape Town, carried out a postdoctoral fellowship at the Marine Institute in Bremen, Germany, and has 14 years of working experience in marine geology and geophysics. Her research interests include various aspects of quaternary geology and glacier-eustatic sea level change, with particular reference to submerged deposits on the continental shelf. Marine geology, human origins, and human use of ancient coastlines were the focus of her PhD work offshore of Mossel Bay. In order to take samples and map seafloor geology, Hayley is a qualified commercial diver and works on marine vessels offshore. She's a member of numerous ongoing international multidisciplinary research projects, all with a focus on South African records, and has published 60 peer-reviewed papers and book chapters to date. So without further ado, I'm very excited to hear her talk this evening, and I'm going to hand it over to Hayley.
Thanks, Nick. Hi, good evening, everybody. It's strange I can't see you, but from what I can understand, you can see my presentation, which is the most important thing right now. I'm just going to get it going. Nick, is everything good?
Yep, all good.
Okay, great. So yeah, I'm going to talk to you a little bit this evening about how we map the seafloor, some applications of those data in a context of human use and within a transdisciplinary sort of environment, and go into some aspects of our ongoing research on the Paleo Plain on the Cape South Coast. I want to go into a fair amount of context before we get going with all of that, into seafloor mapping though, because it's something that is pretty vastly applied to different aspects of research. So in order to get any geological talk contextualized, I need to just say that geological time is, of course, immense, as most of you probably already know. And the Earth is like a giant recycling machine, actually, with continental plates shifting across the surface and ocean basins opening and closing. I've got a little video here. It seems to be working just fine. It just demonstrates how continental plates shift around the surface of the Earth, of course, massively sped up. On the left, you can see the time scales. And this is a bit of a northern perspective, so I'm going to jump forward a little bit to show the supercontinent of Gondwana, which consisted of Africa, South America, Antarctica, Madagascar, India, and Australia. You've just seen Gondwana break apart and India collide with Asia, forming the Himalayas, which is a pretty spectacular collision. Of significance to South Africa is that the breakup of Gondwana was when the Indian and Atlantic Oceans opened and when our continental shelf as we know it formed. So if you can see my mouse on the screen, I'm sort of running it along the edge of the continental shelf. It's the light blue parts of the map. And you'll notice that it's pretty variable. On the east coast, it's really skinny. On the south coast, it's extremely broad. And on the west coast, it's pretty broad too. For the most part, we have a passive margin, but the Falklands Islands microplates actually sheared away from the east coast of South Africa when Gondwana broke apart. Carved this really steep margin over here and a very broad one in the south. Some of you will be familiar with the look of the geology of South Africa, and South Africa has one of the oldest geological records anywhere on Earth, which is pretty remarkable. And although I definitely won't go into any of that now, I just want to say that this is a wonderful natural laboratory for the geosciences. Our offshore territory, which is marked by the exclusive economic zone, or this black line shown on the map, is actually bigger than the onshore land mass. And this also excludes the islands, which we have too within our EEZ. Zooming into the Cape South Coast, which will be more of the focus of the presentation tonight, especially within this block over here. I just want to go over some broad features of the Cape South Coast. Of course, we all know the Cape Fault Belt, which extends all the way from the west across to Port Elizabeth. And these mountains rise about 2,500 to 3,000 meters at most. The Cape Fold Belt separates the Great Karoo, which is inland, from the modern-day coastal plain. The coastal plain and the continental shelf, though, are two components of one geographic feature, which is only ever separated by relative sea level at any time. So this means that the continental shelf is an extension of the coastal plain. And although the coastal plain is pretty narrow at the moment, the continental shelf is pretty vast. So most of this sort of landscape is actually currently submerged. What you'll also notice on this map is that the Cape Fold Belt, marked by rocks that are mostly green and blue, don't really extend too far offshore on the Cape South Coast. That's certainly the case around Cape Agulhas and just to the west. But to the east, the continental shelf strata are dominated by Mesozoic aged, so it's Jurassic and Cretaceous, siltstones, claystones, and limestones that were laid down as the Indian Ocean opened and the continents pulled apart. So these are pretty young and pretty erodible, and they explain why the Agulhas Bank is so broad and so faint. Marine geoscience is a pretty young discipline within the geosciences, and it only really formed or developed in the years succeeding World War II. Limited visibility through seawater, rarely more than 30 meters or so, was actually the sort of bolster behind the development of this field. So whales and dolphins have overcome the problem of seeing through water using sophisticated techniques of sonar, and as of World War II, so have humans. So we adapted those sonar technologies in order to map out things like sea mines and submarines, and later the data were also cast downward to map the seafloor itself. This map that I'm showing here is the very first map that was ever published showing the ocean floor. It was brought out in 1977 by the National Geographic Society. And what's pretty striking about it is that it really hasn't changed much or been improved on very much ever since then. In fact, even still now, the planets like Mars, Jupiter, and the Moon are better mapped than our very own seafloor. This map was compiled for the better part of 25 years by a lady called Marie Tharp, who took together all of the soundings that were acquired during World War II operations, and she was able to grid a surface of the seabed and show people what it looked like and demonstrate that it certainly isn't flat. Because remote sensing techniques that are normally used to map in space cannot be applied to the seafloor, so electromagnetic waves really struggle to penetrate through seawater, and they become highly attenuated when they try and pass through seawater. So you cannot take remote sensing techniques and apply these to seabed mapping. We still have to mount instruments on ships and steam up and down in pretty straight lines, which is sometimes quite difficult. And we call it mowing the lawn to get full coverage of a section of seafloor that we're mapping. We have 5 different techniques that we use at the Council for Geoscience, but I'll go over some of those a little bit later. So why we map the seafloor, part of it, there are many reasons for mapping the seafloor, but one of the reasons is for looking at a context of global change. So sea level is rising, the earth is warming, and these are certain consequences of one another. To quantify future fluctuations and expectations, we have to understand the past. In geology, the present is the key to the past, but if you turn that on its head, you have to understand the past in order to look to the future. Globally, about 600 million people live within 10 meters of sea level, and coasts are really important for GDPs. So in order to know what might happen, we've got to look downward. So at the CGS, we have a marine geoscience mapping program, which is a government-mandated project to map the whole exclusive economic zone. We've done less than 5%, which is pretty scary, terrifying actually, but it's an exciting prospect as well. We want to do this as well as we possibly can and use a term that the USGS coined, which is to map once and use the data many times. So be sure that we do it properly now, as we don't have to repeat this in 10 or 15 or 20 years. And we want to produce what I'm calling the real map of South Africa that includes the offshore area as well, and make seamless maps that extend onshore and offshore for the entire coast. An example here is from Mossel Bay. This is an onshore-offshore map, still in process, but we would like to have things like this that extend across the entire coast of the EZ. I'm going to show you a couple areas that we've been working on before I get onto the Cape South Coast. And one of them is Table Bay, just on our doorstep here in Cape Town. This is a multi-beam bathymetry map which shows depths, red being shallow, blue being deep. You can see something of almost a land bridge between Robben Island and the mainland, which Francis Thackeray alluded to many years ago as well in his work. If you look over here at the position of the Black Star, this is where Bruno Wirtz discovered some Acheulean hand axes on the seafloor. And so far, these are the only evidence of any form of sort of prehistoric archaeology on the seabed in our whole country. So that was a really important find. And now with the data that we have seismic data that penetrated downwards, we have bathymetry on the surface, we're able to start to contextualize the position of these hand axes, the environments in which people were living. Another perspective on Table Bay shows the beautiful rock structures of the Malmesbury Group shales. There's about 2% outcrop on land, and offshore there's spectacular outcrops of these rocks. You can see dikes and faults, offsets, and shipwrecks under my mouse over here. Around the corner on the Atlantic seaboard and towards Hout Bay, my colleague Wilhelm van Zyl has been leading a project that looks at sediment distribution and beach nourishment, beach erosion. And a lot of that story actually lies on the continental shelf. Beaches are a tiny little outcrop of a much bigger system of sediment, which is just waves. In False Bay, I've shown the main morphological elements of False Bay, and you can see that it's a really interesting system below the water. There's pretty variable geologies, and John Compton has been quite interested in Cape Huncliffe for some years. We've done a little bit of diving around there, but we need to pick that up again and continue our work. I have a PhD student called Talisha Pillay who's doing some really smart stuff with geophysical data. She thinks in zeros and ones and does things I certainly can't do myself. And she's starting to do the first automated benthic habitat mapping in the country. So she takes geophysical data, looks at the refraction of backscatter, and is able to start linking that to certain biota that are living on certain reefs or patches of sediment. This is really exciting stuff because as we're mapping, if she gets it right, be able to roll it out, means that we'll be able to produce benthic habitat maps. I have another student looking at paleo tsunami deposits, and he's also considering the continental shelf in this system. So just to demonstrate that onshore-offshore link pretty strong. These are some fun data examples of things that we've mapped, such as Dolosa and Richards Bay Harbour, a shipwreck, this is the Katzmaru in Hout Bay. There's a ladder on the harbour floor in Simonstown, scaffolding, granite outcrops, and we were diving on some features that were mapped out on Blood Reef, offshore Cliff. You can see the resolution of the multi-beam is pretty impressive. And the manufacturers will tell you that if there's a teacup that's been dropped off the boats, you'll see it on the seabed. We're yet to find anything like that, but yeah. So I started to look at Paleo Sciences or paleoclimate, paleo-environments, changes in the past few 100,000 years when I did my master's on Blood Reef, which is offshore Bluff in Durban. This is where I grew up, so it was an area that was really close to home. And one of the special things that we found out there was modern beach rock, the youngest beach rock known yet in this area. Beach rocks were thought to have not formed along this part of the coast for the last few thousand years. But in front of the old whaling station, there were harpoon heads, unexploded grenades, and very hectic stuff found, which was obviously dumped out there within the last 100 years. Through this work, during that time, I moved to the Cape, and through that work, I met Curtis Marion and Eric Fisher and Kyle Brown at a conference, and they sort of got me thinking about, they wanted me to come and apply this sort of work on the Mossel Bay Shelf in the Cape. And it's really helped me to see things quite differently and change tack in a way. And I've thoroughly enjoyed the last 10 years of working with them and other people that I've met along the way. So looking at quaternary global change over the last 2.5 million years, sea level shifts constantly. So sea level is certainly not static. And like I said earlier, the continental shelf and the coastal plain are two parts of one feature. So the red bits of this map shown here are the shelves that are exposed during times of ice ages or glacial maximum anywhere on Earth. South Africa is a really good place to study these sorts of things because we have a fairly stable tectonic environment. This is a sea level curve which has been compiled using various foraminifera and microfossil data. And what it shows is that the change in sea level is pretty rhythmic. And you can see here that 0 on the vertical scale is present sea level, 0 on the horizontal scale is time, so it's now. But if you go back in time, every 120,000 years or so, there's a complete glacial, interglacial cycle. So you have a period of warming where sea level rises in accordance and can reach up to 10 or 12 meters higher than at present. Then it slowly falls towards a glacial maximum, and ice melts much more quickly than it can accumulate. So you have these rapid transgressions that lead to the next period. What happens is that beaches, dunes, wetlands, rivers, all the elements of a coastal plain shift out onto what's now the continental shelf. Sometimes they get preserved there as geological features. What's pretty significant about all of this is that for about 90% of the Quaternary period, parts of the shelf have actually been exposed and not underwater as now. Cape South Coast has a pretty rich record of Quaternary rocks, and they've been pretty well mapped above the water by Mark Bateman, Andy Carr, Dave Roberts, my late colleague, and several other people before them too. And they've been quite well dated. Most of them date to those high stand periods. But there was always this question of what happened on the continental shelf. What's up? Maybe help fill in some of these gaps. When you're mapping out these sorts of deposits and looking to approximate sea level in a vertical rock sequence, for instance, at a river mouth or an estuary, what we're always looking for is a contact between shore-face deposits that are laid down under breaking waves and foreshore deposits, which are laid down on beaches. If you can map out that contact, that approximates mean sea level to within about 2 meters. The Cape South Coast is also a very interesting place to study global change from a perspective of ocean current circulation. So on here you can see the warm Agulhas current coming down the east coast and the cold Benguela shifting up the west coast. And the Cape South Coast is something of a mixing zone. It makes for really interesting biodiversity along shorelines, vegetation on the coast, etc. And looking at changes in time of the movement of these oceanic circulation systems, this is a good place to pick up on any of these fluctuations. Another important aspect of the Cape South Coast is the evidence for human evolution. So our species, Homo sapiens, evolved somewhere in sub-Saharan Africa, probably sometime within the last 200 or so thousand years. We know that our early ancestors moved up and out of Africa through the Levantine corridor and the Arabian Peninsula, for example, spread all over the globe. Recent genetic work, which is extremely complex, and there's basically new findings every year, show the intermixing between the Neanderthals, another unknown lineage, and ourselves. But what remains pretty profound is that everyone else has gone extinct, and only we are remaining on Earth. In order to try to understand some aspects of the complexity, look at areas that have these sorts of deposits, and one of them is the Cape South Coast. So from De Kelders to Klaasies River mouth, with many sites in between, Southern Africa has some of the richest archaeological sites from the Stone Age. I'm mostly going to focus on Pinnacle Point in this presentation, but that's simply because that's where we've done most of our work. But at Pinnacle Point, there's a series of coastal caves that have been incised by previous high sea levels, and some of them are shown on these images here. They've been infilled with really thick sequences laid down by people and also by times when people left the cave. Natural systems of erosion and position prevailed. Most of the caves are higher in elevation than 6 meters above present sea level. At Pinnacle Point, the adjacent shelf is about 100 kilometers wide. And the cave records show that there's the oldest evidence for modern cultural behavior preserved in these records, going back to 167,000 years. There's also been a strong reliance on the coast right through this time. And what the archaeology shows is that there's a reliance on coastal resources when the sea is nearby, and then people seem to abandon site when the sea is far away. So we came together and decided to find a way of contextualizing these deposits by trying to unravel the marine geology of the area. So treating the coastal plain and the continental shelf as one continuous feature, what we did was we used systems to map out the marine geology on the shelf, looked for evidence of Pleistocene sea level fluctuations, and then tried to see the continental shelf as a terrestrial landscape, soils, plants, people, etc. This idea was first brought into literature in 1972 by Dingle and Rogers, after John Rogers has finished his master's on the Agulhas Bank. And already there, they elucidate what could be done and what possibly should be done. But at the time, there wasn't the existing technology to do so. John Compton readdressed these thoughts and ideas, and he wrote an excellent paper in 2011 that summed up a hypothesis for how people used coastlines during time and how this was related to climatic fluctuations. He also came up with the first vegetation map for the area. So our ongoing work on the Paleo Agulhas Plain is largely inspired by compilations on ecosystems, the Fynbos ecosystem, Serengeti ecosystem, and now we've looked at this lost submerged landscape as a complete ecosystem. We have a special issue in Quaternary Science Reviews, which was published in May, that has 22 papers covering our aspects of the workflow. It also sketches out a model of an extinct ecosystem. So I'm going to get you now to imagine a landscape. So picture the sea being drained, the plug has been pulled out, the continental shelf is exposed. Sea level is 125 meters lower, and the coastline is anything from 100 to 200 kilometers away. We've finally, from 10 years of work of mapping and diving and sampling and all sorts of things, been able to produce a geological map of the last glacial maximum, which is the first that we know of globally. It's been a product of much collaboration and many different marine geoscientific surveys. And yeah, we're pretty proud of being able to show this. I'll go into the different features of it a little bit later on though. So the methods to make a map involved firstly going out and surveying the continental shelf. We did 4 different surveys in high resolution. In highest resolution in Mossel Bay and Fleece Bay, and then more sort of broadly from there outward. We spent 3 months in Mossel Bay back in 2011 doing this on a little boat, working only in daylight hours. And we collected multi-beam bathymetry, side scan sonar, and 2 different types of seismic data. The seismic data penetrate through the seafloor and produce almost like slices of cake that show the stratigraphy, where the multi-beam and side scan sonar give superficial information. We did about 50 scuba dives in the area because there were super interesting Pleistocene paleo coastlines that extend out from the Great Brook River that were left behind from those movements of sea level. Because Mossel Bay is not entirely famous for its scuba diving conditions and more famous for things like great white sharks, we had to take some unusual precautions, and we used shark cages that we had collaboratively with Oceans Research, and we had some interesting tools to take our samples, like big sledgehammers and crowbars and things like that. We also used a lift bag to raise these samples because they weigh about 50 kilograms. I've got a short video here of what it looks like to dive down in Mossel Bay, down a shot line. I'm going to pull it forward. So we have a torch on, and we're following a rope that goes down to the seafloor with a hammer on the end. You'll see that the visibility is not great, but when we get to the bottom, you can make out rock ledges and figure out where to take samples. So it gets darker and darker and colder as you descend. Finally, you're kind of on the bottom when you feel it. It's not always possible to see it. We look around, identify an area to sample, and then we start our work. Following all of those shelf surveys, we also have worked on a collaborative or a bilateral South African-German project for the last 7 years, which is called RAIN. And through this project, we had the fortuitous use of the Meteor, which is a great research vessel, beautiful research vessel that works all over the world. And we were able to take 6 cores that are up to about 6 meters deep, the shelf of Mossel Bay, into the river channels, into the paleo lagoons, and into various features on the shelf. So in all, this slide shows the compilation of some of our data that are used to make the map. These are newly collected seismic profiles, cores shown by stars, full coverage survey in Mussel Bay and Fleece Bay, 50 dives within that area. The seismic stratigraphy was fairly interesting, actually, to unravel on a wide shelf, because everything's kind of, because there's a lot of accommodation space, everything is very widely distributed. So dune systems, for instance, never got to be too high or to reach too much of an elevation, and they were very spread across the shelf, maybe much like the Alexandria dune. The surface data, I'll quickly show you some images of that. This is multi-beam bathymetry. You can see off the Great Bruck River a lot of features which are Pleistocene-aged paleo coastlines, so beaches and dunes that have cemented into rocks. That's where we did most of our diving. They were dated by optically stimulated luminescence by Zenobia Jacobs in Australia. So there are submerged caves offshore of Pinnacle Point. This is a sea level of about 23 meters below present. And there's the geology overlay, and you can see this little embayment, which is exactly the same sort of proportions as the embayments along the modern coast. We did dive in here and look for any evidence of archaeology, but we didn't expect to find any because of the conditions, and we didn't. Around the Great Bruck River, those dunes give a very good indication of the direction of wind when they were laid down. So aeolian systems are strongly influenced by wind, of course, and they were dominant southwesterlies and easterlies, which is much like the present situation on the Cape South Coast. Beaches are preserved too, much more spread apart because of the gradients of the shelf. And rivers, they also responded to the shelf gradient quite differently. So instead of being steeply and deeply incised, they were extremely broad and extremely shallow. So for example, this is the Great Bruck River, part of its channel, and it reached a width of 800 meters at the mouth, which is pretty insane if you try and imagine compared to nowadays what that might have looked like. So pulling together all these data, as well as older data, because we always rely on existing data when you do anything. So to acknowledge Professor Dingle and his team, Dr. John Rogers and his teams, in the 70s and 80s, there was the first offshore mapping program, and they produced bathymetric, sedimentological, and some geological maps of the continental shelf and offshore area. So taking these data, as well as our newer data, where we had higher resolution where possible, I ended up going back to older techniques because doing this in GIS got very complicated. And in the end, I actually, everything was spatially referenced. I ended up printing out about 30 different transparent sheets and actually tracing them on a light table in the Western Cape office. There are coordinates and everything was spatially accurate, but I just had to do that to try and sort of see everything as a holistic image. Ultimately, I then redigitized it and made it digital. And this is the geological map that I mentioned earlier. So zooming into some of the features, this is the present coast, tracking my mouse. Still Bay, Mussel Bay, Plettenberg Bay, Cape Agulhas. The edge of the map is the last glacial maximum shoreline. So it's a depth of 130 meters below present. The substrate of the shelf is made up mostly of siltstones and claystones, which are highly erodible, as I mentioned before. Rivers responded pretty differently with really broad floodplains. The Gouritz, for example, had a floodplain of 18 kilometers wide at certain times. The Gouritz, interestingly, also seems to splay into a delta, which is something pretty unique for the Cape South Coast. And it makes for a different type of aquatic ecosystem and other considerations in the paleoecology. The Alfred Banks are an interesting feature shown in green. And this is a volcano, actually. It was the last puff of activity as Gondwana finally broke apart. So 58 million years ago, the Falklands microplate had a last jog or pull away from the rest of southern Africa, and there was some volcanic activity all the way from the Alfred Banks to Sutherland. And this Alfred Banks would have been an interesting morphological feature on this shelf when it was exposed as a landscape. I'm sure it would have of significance to people. From the geology, I've worked closely with Richard Cowling, and we've done a lot of analog work along the coast to look at vegetation and soil and trying to sort of correlate what soils you might expect on this platform. And for the most part, we expect that it would have been probably quite a lot more fertile than the Cape Fold Belt presently. So where the Cape Fold Belt is made up of poorly developed acidic soils. Offshore platforms seem to have been quite a rich or fertile environment. Looking at some aspects of Pleistocene sea level change that have been left behind on the continental shelf, mostly from times of low sea level, a lot of them from times of falling sea level or regression. We see that there are a lot of dunes on the continental shelf. There are massive aeolian. I mentioned Alexandria dune field earlier as an example. So not necessarily too vertically accumulated like wilderness or something like that, but really broad and pretty low dunes shifting around on this landscape. These cemented dune and beach rocks also show very interesting things in the character of how sea level moved. So this figure, it's from a slice offshore of the Great Back River, and we worked out that from about 140,000 years ago, when sea level was rising towards a period of warming, there was a time when it was rising at about 4 or 5 meters per century, which is 4 to 5 times faster than at present. It's pretty remarkable. And what happened was that the geological record, it translated in the geological record to things that overstepped because they didn't have time to wait and accumulate as it would on a normal coastal system. So within about 2 or 3 kilometers horizontal space, we have a massive pulse of rising sea level. And people were living in this area at the time. So we think that people would have witnessed landscape loss within a lifetime, which is pretty profound if you think about it. Going into the post-glacial marine transgression, which is the last transgression from the last glacial maximum to the present, sea level also rose relatively fast, and there were certainly meltwater pulses or times as well when it rose much faster than it present. And there are these fast rises of sea level on the average trajectory. Things that are already there get preserved. And this has happened off the Mossel Bay Shelf too. There are places where paleo lagoon deposits from much earlier before have been preserved because sea level overstepped those and rather didn't stay and erode them away. We also, through the RAIN project and the marine cores that we've taken, we've done quite a lot of paleoclimatic work. And what's pretty interesting about the Gerrits core, which is just directly off the Gerrits River and a water depth of about 40 meters, we had a really good accumulation of sediments that have come out of that river with time and been mixed with ocean systems too. And 2 things of interest that were discovered within this core were presence of the medieval climate anomaly, which was a period of warming, which was previously thought to have been a northern hemisphere phenomenon. It's possibly at the time of when the bubonic plague spread across Europe, and the north was quite a lot warmer. So we think the south was quite a lot warmer too, and it might have been a global phenomenon. Likewise, the Little Ice Age, about 3 to 650 calibrated years BP, was a period of cooling, and this equates to times in the historic record people painted ice skating on the Thames and things like that. So yeah, some northern events seem to be preserved in the south too. We're working on some sea level curves for the area using these marine cores and using shelf data that we have. There have been sea level curves made in the past, of course, for South Africa, but these can constantly be improved on as we get more data. The modern marine sedimentation is pretty interesting too. So the general trend along the Cape South coast is that the prevailing currents move in from the southwest towards the northeast and push sediments around these hard rock embayments. So sediments accumulate in the lee of hard structural sets. And this is exactly the case in Mossel Bay as well. Sediments reach a thickness of about 15 meters in the bay, and they shift around according to different seasons too. Looking at some elements of the emergent shelf as a former landscape surface, which is the sort of interpretive direction and the more collaborative direction that our research is taking now, we see evidence for a wet environment. So there's submerged lakes on this shelf. Some of them we've dated and we're studying them. This lake shown here is from a sea level of about 35 meters below present, and it has exactly the same dimensions as Lung. So it's 2.5 kilometers long, about 500 meters wide. We're also working with Gavin Rishworth from Nelson Mandela University and Renzo Peresinotto, who are specialists on stromatolites. Stromatolites are the oldest form of life on Earth, and these appear in South Africa. You can see them in Barberton, in mountain land. from times of about 3.5 billion, 1,000 million years. They're blue-green algae, and they're the first form of life on Earth as the atmosphere became more oxygenated. These were long thought to be extinct, but in fact they're still living. And there's several examples of them along the wild side of Port Elizabeth, around Cape Recife, Schoenmakers Kop, Seaview, etc. They also occur in Morgan Bay and further north of Ponderland. But these are really important ecosystems because they provide fresh water to coasts. And taking into consideration those broad, shallowly incised rivers that we expect in the Paleo Plain, those would have had sizable estuaries that aren't necessarily available as drinking water to people. So things like stromatolite systems would have been super important. And we think we've mapped out some structures on the shelf that resemble stromatolite barrage pools. Pulling sea level down through time is something we can do with geophysical data. And what's pretty interesting to see is that the coast that's currently embayed along the whole Cape South Coast becomes increasingly linear as you drop sea level. So at 18 meters, 30 meters, 40 meters, the coast still has these little embayments. But below a depth of 47 meters or so, we expect long, straight, or more straight, sandy beaches. And this is interesting because it impacts on the nature of the systems and it impacts on shellfish in the system. We have had a unique opportunity to compare low-resolution geophysical data from offshore to very high-resolution archaeological data from this Pinnacle Point caves and from other caves in the area. We've looked at Blombos too in this regard. What we see is a pretty good correlation between the nature of the geophysical data indicating a type of coastline to the kind of shellfish that we find in the archaeological sites. So, for example, at 112,000 years ago at Pinnacle Point, drop sea level to the elevation where it would have been, and see that the geology shows there would have been a dominance of Table Mountain Group sandstone, rocky shore, as well as unconsolidated sediment, sandy shore. And this is really cool to see that at the same time in the caves, people were exploiting Donax sera, which is white mussels or sand mussels, olycrical, and brown mussels. So a range of different coastal environments. Also using the geophysical data to look at sourcing stone tool materials on the continental shelf. So things like cobble beaches, things like hard grounds like calcrete, possibly silkweed. We're looking for these things on the shelf and trying to see the radius from the cave that people might have been able to. There's evidence of soil on the shelf from the marine cores, and in this case, there's some hematite shown over here. The soil data combined with geological data and climate data that's also been modeled for this bigger project was worked up mostly by Richard Carling and his team. And from the geology, we're pretty sure that there were grasslands, extensive grasslands on the shelf. The soil models came up with similar findings. And vegetation models are showing a system that's pretty different to most of the Cape South Coast nowadays. And this is pretty pleasing because the archaeological sites along the Cape South Coast have long had a pretty odd, if you could say, faunal assemblage record, where the faunal assemblages in caves from animals that people were eating are largely composed of grazing animals, and there's nowhere really that they could live in the Cape Fold Belt Mountains. So we think that when sea level falls, there's a totally different plains kind of ecosystem out there, and this might make sense to see what animals were living in that area. Also on vegetation, Adriaan Grobelaar, Richard Carling, Alistair Potts have been working on the coastal Strandveld, which is one of the elements of the fynbos biome. And something that's always puzzled Richard is that the Strandveld is so biodiverse, it's so species rich, but it's such a tiny, it occupies such a tiny area now. So at the moment, it only occupies 1.2% of the Cape Floristic region. But when you drop sea level and consider those massive dunes and the wide shelf, it makes sense that it would have been much more broadly distributed. So at the moment, we're just seeing a small sample of a much larger floral system. Looking at back to animals, aside from the faunal assemblages and archaeological sites, Dr. Charles Helm, who's a very good friend of mine and one of the great colleagues on this project, he does a lot of work on trace fossils. He maps out trackways along the coast in the modern day Aeolianites. So Charles has mapped really interesting animal data, which is great for trying to reconstruct paleoecology. So some of the examples of Charles's work is that he's found hominid footprints at Benton on Sea, longhorn buffalo that's now extinct, Cape lion, giraffe, which was an excellent paleoecological indicator. The giraffes were found near Still Bay, giraffe trackways, and this was really quite surprising because you wouldn't expect that giraffes would be able to survive in the modern day Cape. But if you look at the geological maps and the soil maps, those broad rivers and their very wide floodplains might well have been associated with riparian vegetation and savanna ecosystems. And this is very closely linked to what giraffes would require. So he's also found crocodiles, elephants. There are quite a few elephant trackways along that part of the coast, rhinoceros, and baby sea turtles in the last interglacial at Still Bay. Together, combined with vegetation, combined with cave records, we're starting to get a really good idea of this ecosystem. Coupled with this, Sandy Copeland and Jamie Hodgkins have led some work on isotopes, and they've looked at strontium specifically. So we did a survey across the Cape, Southern Cape, right to the Kangaroo, sampling every single geological unit and its soils and its plants, trying to figure out the bioavailable strontium, and compared that to strontium in animal teeth from archaeological sites. What the study showed is that a lot of the teeth that are preserved in archaeological sites corresponded with strontium values that must have come from an area which is now underwater, because it didn't match with most of the modern values along this coastal plain at all. So bringing it all together, we think that the closest analogue of the Paleo-Agulhas Plain might just be a small area, 70 square kilometers on the Agulhas Plain, which is between Bredasdorp and Cape Agulhas. This is compared to about 40,000 kilometers, which is 40,000 square kilometers, which is now under the water on the continental shelf. And it might be a very small element of a much bigger system, which could have been something a bit like this: meandering rivers, grassland, wetlands, small dunes. Maggie Lambert Newman did this painting to try and depict the Paleo-Agulhas plain landscape, showing people and aspects of their cultural lives from archaeological sites, animals that they would have been using for various reasons, and the landscape that we expect to have been prevalent. So to sum up, what we now know about the Paleo-Agulhas Plain is that these geological deposits on the emergent shelf indicate a greatly expanded glacial coastal plain. There were shallowly incised, broad, meandering rivers that flowed on the shelf, extensive wetlands, and a water table close to the surface. We've reconstructed ancient habitats and linked that to faunal assemblages and paleoecological signals. And we definitely can say that the submerged portion of the Paleo-Agulhas Plain is not featureless, as it was sometimes suggested. We think it's a plains kind of landscape that was much more fertile than the current Cape Fold Belt foreland. So from here, just to say that our work on this project is, for the most part, extending towards the east. So we've considered the western part of the Agulhas Bank. We're now looking at the eastern part of the Agulhas Bank, Algoa Bay, St. Francis Bay, Titicaca Coast maybe, starting probably in Algoa Bay and working towards the west from there. This is where we're going to focus our offshore mapping and a lot of our coastal work as well. I work on quite a lot of science to policy projects through the Council for Geoscience, and those are always ongoing. And I think that that's great because we can take what's happening in the natural sciences and hopefully it translates into useful policy for people in South Africa. And then besides focusing this work on the east, I'm also very involved in a Ponderland project, which Eric Fisher might present to the Society in September. Ponderland is situated on the Wild Coast, and we've been working out there for about 9 years or so. We found some fascinating stuff. So we were looking for a sort of similar setting, not similar in the sense of ecology, but similar in that you expect rock shelters and caves close to the coast, incised into old, cold rocks. And in Ponderland, the Mcicaba Formation is very similar to the Cape rocks, except that it's not deformed and folded. But Ponderland has a continental shelf that's extremely narrow. It's less than 10 kilometers wide. So we were hoping to map out the last glacial maximum in the neocoastal caves to try and get a better picture of what people were doing at the sea levels. And so far, this has been really successful and really interesting. There were really great resources available to hunter-gatherers at the time. And it's a really fun comparison to the Cape South Coast, which is pretty different. So with that, I'll wrap it up and have lots of friends and colleagues and collaborators that I wish to acknowledge. None of these projects are ever done alone. So yeah, that's all I've got for you. Thanks, Nick. Oh, wow. Oh, so the giraffes are generally an indicator of savanna sorts of vegetation. So instead of it being something like the Nasna forest or the Titicaca forests, we expect that it was probably savanna-like trees growing along the floodplains of these sizable rivers. So something that doesn't have a modern analog on the Cape South Coast right now, because at the moment the coastal plain is pretty steep and pretty steeply dissected by rivers. But as soon as you get out onto the continental shelf to times that correlate to depths that are deeper than about 25 meters, everything is pretty different and pretty flat, low gradient, clay, stone, siltstone, different trees, different grasses. So we expect that the giraffes are probably living in a slightly different ecosystem to what we have anywhere around there now. Oh, sure, no problem. So from the geophysical mapping, what we've got a very good database now from the last several years of doing this of identifying different rocks based on their textures. So before we even go diving, often when we're processing the data, based on the types of returns we get from geophysics, we can pretty much sketch out a rough idea of the distribution of different kinds of rocks. We then ground truth those by going diving, taking grab samples, taking cores, and validate the ones that we're unsure about, but basically validate as much as we possibly can. Hopefully everything, normally everything. So yeah, so we look at sound waves and their behavior, and then we sample the rocks as well. Okay. Yeah. So uh, east of Cape Agulhas, The only area that we found along the coast that we think is a very good analog is that Agulhas Plain. So one small area between Bredasdorp and Cape Agulhas. That's pretty much the only area that we think is a very good analog. But all of the different geological deposits that occur on the continental shelf also have examples on land, not necessarily in this area though. So there are elements of that landscape that we could go to and look at and show people and study things like the soils, but they're not necessarily in the same context. I don't know if that makes sense, but sorry, just on that. Sorry, I just wanted to add on that the Cape Flats would be an extension of the False Bay seafloor. So what we would expect to find out there on the False Bay seafloor would certainly be things that relate to places like on the Cape Flats. So often you look at adjacent environments because there's a lot of fluctuation in climate, environments, ecology. So you might have the same geology on each side of Cape Agulhas, but because of the different ocean systems, the different climate systems, the resulting composite ecosystem might be quite different. Oh, not very well at all. Pliocene is actually, it's a fascinating time, and there really hasn't been that much published on that. Best example of Pliocene work that's been done is, of course, around Langebaanweg and on the west coast. Further northwest of that, there's a lot of evidence of those Pliocene sea levels, but mostly within diamond concession areas. So they're really difficult to access and to be able to do research there. My late colleague Dave Roberts did quite a lot of mapping of Pliocene terraces, and he found that for the most part they correspond to heights above present sea level of 30, 50, 70, and 90 meters, which is significantly higher than at present. He wasn't sure if that went back to the Miocene as well. I think that might be likely. But in short, the Pliocene deposits have been not very well dated, not very well constrained at all. Yeah, I can, Nick. Yes. Okay.
I didn't click on update. Sorry about that, guys. I think I've managed to fix my audio now. So those questions, I'm going to just repeat them, and just so that you guys can get on the same page. They were in the chat box, but we had Belinda and Andy's question about the giraffe footprints was the first question. We had Andrew Kendall's question about the kinds of rocks on the sea surface. And then Hayley answered the question from Ronnie Glass about the sea level and what interesting things have been found. And we had one from Vincent Hare, which was about the how well do we know the Pliocene Paleo sea level fluctuations relative to the Quaternary. We got one more question, and that's also from Ronnie Glass. And he's asking to tell us more about the cycles, the times of each high and low. So if maybe you could just repeat that back just in case my audio isn't coming through.
Yeah, sure. So just to repeat the question that came now from Nick, is that Ronnie Glass asked about the timing of the cycles, the high sea levels and the low sea levels. So a complete glacial interglacial cycle generally takes about 125,000 years. This is linked to orbital parameters. So the position of Earth relative to the Sun and the shape of the orbit, the time it takes to complete it, and also the tilt of the Earth's axis. These are Milankovitch cycles, and they are precession, eccentricity, and I can't think of the name of the third one right now. But anyway, so Milankovitch cycles define the length of these glacial interglacial cycles as a whole, and also the fluctuations within them. So you have about 125,000 years from sort of peak period of warming to the next peak period of warming. And within that, there are fluctuations generally on the way down that are within cycles of about 41,000 years and 23,000 years. So interglacial periods are pretty variable. The last interglacial period, which was 125,000 years ago, it lasted probably about 5,000 years, and sea level was about 6 or 8 meters higher than at present. But the worst case scenario that we would expect to experience now is actually linked to marine isotope stage 11, which is 400,000 years ago. And sea level was about 11 to 13 meters higher than present. And that interglacial period lasted for about 10,000 years. So it takes about, let's say at worst, a period of warming is about 10,000 years. Sea level takes about 80,000 years to drop. The glacials, the ice ages might last 5 to 10,000 years as well. And then generally it's a very quick rise to the next period of warming because ice is much easier to melt than it is to accrete. So the timing from a glacial maximum to the next warming is usually about 20,000 years. I hope that explains it a little bit.
Yeah, I think that covers it well. Thanks, Hayley. I think that's it for the questions. I think I don't see anything else coming through the chat box. Last chance, guys. Anyone for a last question? But I don't think so. Yes, that was really, really wonderful. Really appreciate you spending time this chilly evening in Cape Town. I really appreciate everything you've prepared for the talk, and I think the members really loved it. We hope to catch you on our talks in future as a member. I believe you've just joined the ArchSoc Society. Yeah. So, we're looking forward to seeing you hopefully one day once we're out of lockdown.
Perfect. Thanks, Nick. Yeah, I'm excited to be part of the society now too. And thanks everyone for tuning in and listening. It's always weird doing these things remotely, but it was a pleasure to be able to do this presentation for you. Yeah.
Wonderful. Yeah, and thank you to everyone for coming. We had nearly 60 people who joined the session this evening. And as I say, we love your support, and we will catch you guys all in a month's time. Have a lovely evening.